So here we go. I'm gonna present you part of my PhD and on the estimation of specialized turbulent flux on flux towers and its uncertainties. And yeah, thanks for the invitation. It has been a very interesting first talk. So first of all, for context, of course, we are talking about climate change and it's happening now, and we need to measure to understand the impacts. So in here we have temperature and precipitation for average and extreme events in a scenario plus 4 degrees. And we just to see that things are changing everywhere and differently. So we need to be measuring them in here, temperature and precipitation, but this will of course affect sources and sinks of CO2. So how do we do the measurements? We apply, for instance, it depends on the scale that we are interested. So it can go from leaf to the globe. And talking about the globe, so we have the satellites. The satellites are very important too, but they lack in spatial density, and they still have to solve the vertical profile. And to do that, what they use is mostly atmospheric data for the inversion. But this inversion needs a prior, and this prior comes usually from ecosystem data. And so that's the path. And in this, I'm going to be talking mostly about these two, and the goal is to improve this prior, also doing an inversion. And of course, since these flex towers became very popular, nowadays they are everywhere, but not consistently. We need to be more global to be measuring all the effects that we see that we know that climate change will be impacting different places, just a very brief explanation of that covariance, just to give you an idea of what I'm talking about. We have instruments that are in a tower at a certain height, and what we are measuring comes from the wind, so it's transported and mixed through the wind. And basically with the covariance of the vertical component of the wind and our gas concentration, so in our case, usually CO2, we can have a flux. This represents the surface flux. And so as we are measuring at some point, we are usually, there's this, where it comes from is what we call the footprint. And so it depends, of course, on the wind direction, wind speed, etc. And I'll explain all that because nowadays standard eddy towers have usually one target ecosystem. So in here we have a map of Île-de-France, and we have these two towers, one agricultural in Grignon and another one in Fontainebleau forest. And we can see that in both cases we have a tower in the middle of the forest, in the middle of the site. And that's to assure that at any point of time, we are always measuring the same ecosystem that we are interested in, and we expect them to be homogeneous, so we don't have to think a lot about the footprint all the time. However, this becomes more complex, and in here I'm gonna do a parenthesis. The idea is that we are going towards urban environments, and we getting more complex actual landscape that we want to be measuring. And so this is a parenthesis because we are still needing the setup to be ready, but this is one of the final goals of my PhD, is to actually decompose the contribution of each climate zone, so in an urban, peri-urban site, to the measurements of a tall tower. And so to actually, at a certain point, arrive at this result, the first step was to apply the method in a smaller scale to better understand. So in here, and the goal is to provide a method for scaling turbulent flux towers measurements using fine resolution remote sensing and inverse modeling. So basically we have the surface flux that are measured by eddy covariance or other methods, but in these flux towers. And they should correspond to this estimation that is based on surface model. That depends on the landscape. It can be light efficiency models, can be the inventories. And also they should include in the footprint, we can see what the tower should be measuring, and comparing the two is what I will do next. And since we have two values that we can compare, we could do some regression, for instance, but we can also do some inversion. And in further slides, I'm going to explain briefly how and what. And the basic idea here is that to first test, we apply this to a null site. It's going to be Grignon, and the idea is to have the minimal anthropogenic influence. So to get the biogenic component ready to go, and then because it's the most important and complex, and so then just add the inventories and add all the other components. If I just go back to better understand a complex landscape such as we see in the right, which would be measuring a lot of different things at the same time. So advancing, yeah. So what is the kind of light efficiency model that we're using? In here we have the VPRM, which includes some tower data, some also satellite data to do this estimation. So we have on one side the photosynthesis, that is basically a parameter lambda multiplied to the temperature and water conditions, a proxy of LAI, which will give the density of foliage on a given ecosystem, and the light sensitivity. On the respiration, we have a parameter alpha multiplying temperature and plus a beta that shows the minimal, the continuous respiration that doesn't depend on temperature. And so I highlighted these three parameters because they are the ones that I'm gonna optimize. Also, yeah, and for the inversion, as we do it now, we need the parameters to be optimized to be linear. And so that's why why we choose these three ones. And so there are some updates there, as we see on the left. In 2008, the surface reflectance came from Moody's. Nowadays, we have Sentinel-2. This is very interesting because even sites that are in small scale, for instance, the Grignon site, the agricultural site that I showed a picture just a few minutes ago, we can with Sentinel-2, so 10 meters per 10 meters pixels, we can still see we can still clearly see the site with a lot of pixels and do some interesting work that I'm going to show. And so in here we have in the right the EVI that will work as a proxy for FAPAR. And we can see the difference between June and the end of July. And this is basically the satellite in here will work to resolve this temporal and spatial information of crop growth, for instance, or for growth of leaves, and the harvest, for instance, if we're an agricultural site. The inversion strategies. So the goal, first of all, is to find the best parameter to move the estimation towards observation, considering the prior knowledge of the system and the respective uncertainties. So different from a regression, we are also including the uncertainties, so where we can trust more or less the parameters or the observations. And so in the right, we have this cost function, and that's what we are trying to minimize. So basically we have these two parts. One part is for the parameter and another one for estimation observation. And once we get the estimation far from observation, we increase the cost, and the same for parameter, comparing the new parameter with the prior. And so we want to minimize both of them. And so that's where it comes this second equation with the estimation or optimized estimation. And we have the innovation and a relaxation to incorporate these uncertainties. With that, we get the flux map that we want. And also with this method, we can have the uncertainty. So to be very brief, we have this covariance matrix that will give us the variance. And with a Monte Carlo approach, for instance, we can run it several times and get some kind of variance of the system and the uncertainty. So I just before I talked about Grignon, and I said that I presented as a homogeneous site, but we know that this is not completely the case. So in here we have study from 2004 showing the yield of the site, and we showed we can see clearly that there are differences. There's a large spatial variability that's most probably linked to the water content. And so when we run the inversion and all that I showed just now, we get these maps on the right. This is for another year, for another crop, but we can still see the same kind of spatial correlation between both, indicating that this should be something that is intrinsic to the site, to the soil, and showing the importance of also understanding these heterogeneities. So here we just showing some that the model captures actually the dynamics. So we have in here we have the whole from seeds to the harvest. If we can see that the maize only starts to grow here mid June. And we can see if in the bottom figure is the same, but it's more, we can see better. We have the first guess, so this is the prior, this is the estimation using the parameters that comes from literature. And we can see that it poorly represents the site. I mean, there is some connections, but it's not the same magnitude. And when we do the Bayesian inversion, we get the good estimation. And so yeah, in here it lacks the uncertainty for the estimations, but this should be actually smaller than the uncertainties of the both observations and parameters. And moving on, what I just showed is we did the optimization for the whole time series. However, we can do the optimization month by month just to check if there is a varying, the parameters will change and etc. So in here, that's what I show. We have on the top part, we have the parameters and per month. And then we can see that when is the continuous line is what I just showed before. Sorry, when it's a dashed lines is what I just showed before. So we can see that it's constant for the whole time series. When it is a continuous line, then it's I inverted monthly to get the variation of the parameters. And we can see that for the blue one, so it's lambda, there is this line small decline for which for us, so the lambda is what interacts with the photosynthesis part. This could indicate that the crop becomes less responsive to the climatic variables, but it could also maybe be a problem with AVI saturation. We still have to cross. On the other side, for respiration, we have alpha and beta, and we can see that there is a slight compensation. There's one that increases in July and August, and the other that decreases. But this could also indicate that there is actually temperature is losing its importance. Let's put that this way, and maybe other climatic variables are becoming more important. This is 2019 is a year of with heat waves, so that might be the case for these 2 months. So we have also the estimations, the mean estimations for the different months. And I will try to conclude to give more time for the discussion. We can the surface model allows us to have the spatialized flux, but we need to calibrate that, and that's why we use the inversion. So the 2019 flux maps, they correlate with the 2004 yield. So this indicates that this approach can give a good intrinsic spatial variability of a site. And we can so we can better understand sites that previously were taken as homogeneous. And also, so GPP, so response decreases when monthly calibrated. This is possibly linked to the phenology or the EVI, as I just mentioned. And an increase in respiration can be, there's an increase in respiratory response to temperature. Sorry, it's a decrease actually. But there is a parameter compensation in this part, so possibly indicating how the factors play a role. And for some perspectives, so we should be in the next steps or to use this in different years, 2019, 2020, and 2021. We're going to have different cultures being grown. So we can compare if it's if it's robust, if it repeats itself, this spatial pattern. Also on different sites, crops, forests, and grasslands. And we should be validating it with the biomass and soil carbon stock. That is maps that are available for that. We just have to be careful with the scale because it's in this case a small site. And also, of course, this is the other big part is that satellite resolution is increasing. So we need to be doing these observations also in a more precise way. So we're currently working on decreasing the time averaging. This should decrease the footprint. And so this would gain kind of precision on the source area. And also we are trying to decrease the gap filling to increase the number of data points. And with all that, I thank you, and I'm open for questions.
Thank you, Pedro. So we can take indeed several questions. I see a first question from Marie J. What does the GEE stand for?
Okay. Gross environmental gross ecosystem exchange. So it's basically the sum of all the photosynthesis and the part of the plant side of the carbon cycle.
Yes, thanks. It's because I got disconnected for a while, but I caught up afterwards. Thanks a lot.
Yeah, okay.
Can I actually ask another question, or should I raise the...
No, please ask.
Okay. What type of spatial resolution for sat images would be good for you, if I can ask it that way, or if you could have any spatial resolution and spatial and temporal, what would you like to work with? I'm not a salesperson. It's not a trick question. I'm just interested.
Yeah. I don't know, in a dream scenario, like having 1 meter every, I don't know, every 1 day would be awesome, but I don't think this would be possible. But the idea is that so since the model includes some climatic variables, we can catch, for instance, day and night differences and things that a small event with increase of temperature, etc. So in here, the satellite is really to give the long-term, the mean variability. And so I would be increasing mostly to 1 meter resolution and shorting to at least one good satellite image per month. And this would be a more realistic and interesting.
Thanks.
Other questions? Difficult to see everybody at the same time. I have one concerning the use of the Bayesian methods. You were a bit fast for me on this aspect of your work, so maybe you can explain it a bit better.
Yeah.
If you may.
So, okay, yeah. So basically, the Bayesian inversion would be defining this cost function. Once we define this cost function, and I can explain a bit better, but once we define this cost function, then there is no more, let's call it, science behind it, because then it's just minimizing it. And so to get from this cost function to something that looks like this one, the parameter optimized equal to this equation on the bottom. Then this, if it's a linear relationship, then there are some simplifications that we can do. And there's a whole, but it's all very mathematical in the sense that you just follow the rules and the equation simplifications that we can do, and then we arrive at this. So the whole the science part is really on choosing this function and choosing your uncertainties. And yes,
and how do you do that? How do you choose B and how do you choose R?
So that's, yeah. For us, the uncertainty linked to the observation is actually we already calculate this. Like in standardly, we already measure that with calculate that using the random, what we call the random uncertainty of eddy covariance. So these, we have perfect signals that we have an idea of how it should behave, and then the difference between this and what we see is in the frequency aspect. We can relate that to this random uncertainty. And this is, for us, this is what we're using now. This is our observation uncertainty, and this is the most important one. For the other side, the parameter, what we are doing now is a very simplified approach. We just put 10 or 15% of the parameter that we used as prior. There are other, yeah.
And
but
so you obtain
it is the heart of the inversion to get these uncertainties right.
Yes, I can imagine. And okay, thank you. I see another question in the chat, I think. So I think it's a technical question from Amadou. Maybe Amadou, you can ask a question directly if you like.
Hello, Pedro. Thank you for your presentation. I was wondering if there is any difference between the growth ecosystem exchange and the net ecosystem exchange.
Yes, the main difference is the first word. So one is gross and the other one is net. So when we put the net ecosystem exchange, this becomes the net result. That's what we are actually measuring, and it means the combination of the respiration, photosynthesis, and all the events that are happening on the surface. This is different from growth, because the growth will just take the plant side of the carbon cycle. So this would the growth in this GEE is not including, for instance, the soil respiration, which is a big. And when we see the separation here, we can see that it will cut down for some in here in orange. It will cut down.
So you consider just the soil respiration just minimized during the growth period.
Sorry, can you repeat?
I was saying that in your estimation of the growth ecosystem exchange, you just don't consider the soil respiration.
Yeah, but this is included in the relation, the linear, in this linear relationship between alpha times. This should be included here, respiration.
One more question regarding the minimization scheme. I'm not sure if I got this right. In the first part, in the cost function, this x minus the xb, is that basically a penalization of parameter change per iteration, or I don't really get the first part of this. Exactly, this parameter penalization.
Okay, so that's the idea is that, so it's a cost function. We have these two sides. I'll briefly explain. Just estimation and observation is very easy to understand. We want an estimation that is very close to the observation. If it's far away, we don't like it, we increase the cost. So I said that because the parameter is the same idea. we want, if we have a prior knowledge of the system, and then the optimization will give me a parameter that has nothing to do, is completely different, then it's completely ignoring the previous knowledge. And this is kind of what happens when you do a simple linear regression. You just find a number, but it's not including the prior knowledge of the system. So that's what it means in here, this part. We want something, we want an X that resembles the prior knowledge, so the parameter that we put in the first place, and we want something close to that. Of course, which one is the best one to get a parameter that is very close to what we had before, or to have an estimation that is very close to the estimation, very close to observation. The question between both will be weighted based on the uncertainties. If we are very sure of our observations and not sure about the parameter, then we'll move the balance to the other side. If we have parameters that we are much more sure and observations that are not very good, then we will try to have optimized parameters that are very close to the prior knowledge of what we put in the system.
I have another question here on the assumptions you make. So basically, here you assume Gaussian distributions both for the prior and for the likelihood function. In that case, indeed, the result is the posterior mean yeah. So, but is a Gaussian assumption realistic in your case?
That's a pretty good question, very technical. I think this assumption is done. It's very commonly used in these Bayesian inversions, and it is like when we talk about Bayesian inversion, it assumes that actually. So it's very much used, and then I didn't cross-check it specifically for my inversion. And this is something that the next 2 years, we're going to be crossing that and recrossing that to better understand. But I would say that it's a safe bet to do it, at least for a first putting this assumption clear in the paper.
Yeah, I guess you also assume independence between the observations in this function, unless you have a matrix, variance covariance matrix somewhere, but I don't see it in your formula. But
actually, so yeah, actually, it's not completely true. I can have in the whole thing plays in the uncertainties. So the uncertainty is going to be a covariance matrix. And so what I do, actually, I didn't put it very clear. I also include the uncertainty for the parameters, but I include some kind of connections. In this case, we are only applying the whole site as one only pixel. But if we would be applying this as different pixels, then I could include saying that one pixel, the pixels that are close to each other, they should have something that is similar to each other. And this is something that we have already done, and it works. It works.
Very good. Okay.
There is some. We can find this linkage between. This is completely off because I didn't present, but we can see these correlations between parameters when we optimize different pixels. I do the inversion per pixel, and we can have some also. There are also some problems due to the observations, the footprint, but well, I'm not getting into that. But...
Okay.